Throughout this series on power system protection, we've seen that protective relaying has developed into highly sophisticated schemes which are very adept at performing their job. That is to automatically detect faults and trip out and isolate the responsible circuit or section. In general, these protection schemes are discrete in nature. They operate to protect their own section of the power system with little regard to what's going on elsewhere. Alongside this development of protection schemes, another system has evolved with the objective of providing an overview of and supervisory control over the power system. Note that this system is concerned with monitoring and control as distinct from protection. As its name implies, protection is really a last-ditch action which disconnects some part of the system in order to protect equipment from damage. The result is usually an outage, which may cause some disturbance to the system and perhaps to customers, if only for a very short period. Supervisory control and data monitoring, on the other hand, is concerned with providing the system operator with remote information and control facilities to assist him in operating the power system in the most reliable, efficient, and economical manner. Supervisory control schemes come under different names, such as energy management systems or energy control systems, distribution automation, DACS, which stands for Data Acquisition and Computer Systems, Scada, which is Supervisory Control and Data Acquisition. There are probably other terms, but we'll use the term Scada as a generic description of all of these control schemes. In the first segment of this videotape, we're going to discuss the principles and application of Scada systems. Of course, system operators are the prime users of Scada, but it's also important that relay and control technicians become aware of the applications as well. After all, they're responsible for maintenance, testing, calibration, and modification of the system when required. Subsequent segments go on to look at typical installations and hardware. We'll be looking at generic features of recent installations. You must be able to apply these general concepts to the specifics of your own installation. The essential features of all Scada systems are the continuous collection of information related to current operating conditions from many locations throughout the system, transmission of this data into a central computer, which is programmed to evaluate and make appropriate decisions, display of this data to allow operator interface, transmission of control command signals from the computer to a remote station in order to initiate action based on operator or computer decisions. The advantage of this scheme is that the computer is acting upon data which represents operating conditions throughout the whole system at that moment. Of course, the operator has always had to do the same thing, but we must admit that the computer is much faster than you or I at digesting hundreds of pieces of information and deciding appropriate action. Let's look at a few typical applications of Scada. First, in energy management of the high voltage power system. Typically, an energy management system, EMS, is used to monitor load and reactive power flows at different parts of the system, including power stations and interconnections with neighboring utilities. Based on programmed economic dispatch data, the master computer will assist the dispatcher in determining where to generate active and reactive power. In some cases, it will issue appropriate commands directly through the Automatic Generation Control, AGC, to the generating stations. It will also continuously update the loading schedule and assist the dispatcher in arranging unit commitment. The EMS may also perform interchange calculations to help the operator decide when to buy or sell power. It can also collect billing information and print out routine operating reports. As EMS systems develop, the trend is to increase the degree of automatic control in place of just operator assist. On distribution systems, the Scada system is typically used to implement load shedding and load management schemes. Another distribution application is in the automatic switching of feeders in order to achieve the most efficient configuration. That is, to equalize the loading on feeders and so reduce system losses. Clearly, there are many other applications. In order to support all of these schemes, there is a need for a vast number of measuring points located throughout the system. In addition to this, we need a large communication network which is capable of accurately transmitting all of this data to the central control computer. In fact, it is only with the development of modern communication methods that Scada has become feasible. The data is first collected by remote terminal units, known as RTUs, which are located in substations throughout the system. In some cases, small RTUs may be mounted on distribution poles in isolated areas. The RTU is essentially a microprocessor which can store and process data in digital form. This information is received from monitoring points which measure conditions on nearby equipment, such as transformers, circuit breakers, transmission lines, and feeders. This data typically includes measurement of analog quantities such as frequency, current, voltage, real power, reactive power, and so on. Additionally, equipment status is also monitored, for example, breaker open or breaker closed. Where the signals are in analog form, they must be converted to digital for use in the microprocessor. All of this information is stored in the RTU's memory and updated continuously. However, it will only transmit this data to the central computer when requested. The reason for this is that the central computer has to take care of many remote stations, and it does this by scanning or polling the system. Each RTU is identified by its own individual address. The central computer continuously addresses each RTU in turn and receives an update of information from that particular station, and consequently updates its own memory. In many Scada systems, this update takes place typically every 6 seconds. On some installations, in order to further reduce this time, the RTUs report only exceptions, that is, any value which has changed by more than a preset tolerance known as the dead band. This allows the current, say, or voltage to vary within a specified range before indicating an exception. Another exception could be an alarm condition or a change of status, say the opening of a breaker. With this arrangement, it is usual for the central computer to poll all of the stations and update its own memory at 2-second intervals. When the RTU does report by exception, priority is given to alarm conditions or a change in status, so that this critical information will always reach the operator within 2 seconds or less. The operator interacts with the central computer through the CRT terminal. This can display selected information related to any part of the system under his control. For example, he may want to see a scan of all points at a particular RTU instead of exceptions only. The operator can also instruct the computer to print out selected information to assist in operating or contingency analysis. Indeed, the central computer is programmed to regularly provide many reports which assist in load forecasting, system planning, and so on. The central computer may also feed information into an events recorder, which is able to print out the sequence of operating events. Information may also be provided for accounting and billing purposes, for example, accumulated megawatt hours, megavar hours, and maximum demand at specific locations. We can see that data acquisition is certainly a vital function, but what about control? Well, updated information from throughout the power system is continuously passed through a central computer, where it's compared with pre-programmed algorithms, which are based on system operating parameters and variables. The algorithm passes the incoming data through a series of logic steps to determine if and where operating conditions must be changed. Where action is required, the operator is alerted. In some installations, the central computer may directly transmit command signals over the communication network to the appropriate RTU. This, in turn, will initiate the required operation, such as open or close breakers, increase or decrease generator load, adjust generator's excitation, adjust transformer taps. A particular feature of breaker control is SBO, that is the Select Before Operate sequence. Let's see how this works for an operator-initiated action. First, the operator identifies the point he wishes to control through his keyboard. The master computer immediately codes and transmits the command to the appropriate RTU. When the RTU receives the signal, it confirms that the point hardware exists, selects the point for action, and sends a checkback message to the operator's console. This checkback signal allows the operator to verify that the point he selected is in fact the point he wishes to control. It also confirms the status of that device. If this is correct, the operator will issue an execute command, and the RTU initiates the appropriate action. When the action is completed, that is, the breaker opened, the RTU will send a confirmed signal back to the master station. Normally, a time limit, say 10 seconds, is allowed between point selection and execution. After this time limit has expired, the selection is canceled. All right, so much for our brief overview of Scada. We have tried to show what supervisory control systems can do for us. In the remainder of this tape, we're going to take a closer look at the equipment, that is, the RTUs, the communication systems, and the master station. For now, please switch off the tape and review this material in your workbook. Remote telemetering systems, the forerunner of Scada, have been around for a long time. These systems were usually hardwired, utilizing electromechanical relays and analog signals. As a result, they were quite slow, and the amount of data that could be transmitted was limited. For this reason, with this type of system, instead of continuously updating information, it is usual for the operator to request specific data only as required. As an improvement on telemetering, Scada systems developed utilizing integrated circuits to provide much faster response and handling of data. Much of this equipment, installed in the 70s, is still in operation, and no doubt creating maintenance work for many of you. The more recent Scada systems are microprocessor-based, using digital signals. This allows for handling a far greater amount of information and at faster response times. Moreover, the ability to program the software for each specific application means that the system can be made to perform many more useful tasks than the earlier systems. This block diagram shows the very basic elements. That is, the central computer at the master station receiving information over the communications circuit from one RTU. In practice, there would normally be more than one RTU. Depending upon the particular Scada application, we may have as many as 200 RTUs or even more, spread out around the power system and all connected to the master station. Many of the measured signals are analog in nature. For example, the monitoring of line currents, voltage, megawatts, megavars, and so on. For each of these metering points, the AC signals from measuring devices such as CTs or VTs are fed into a transducer, which converts the quantity into a DC analog signal, millivolts or milliamps. But the microprocessor requires digital input, as we know, so an interface is required in the RTU to convert the incoming analog signals to a digital format. This is then transmitted into the RTU memory. We have already discussed digital signals and binary numbers in earlier tapes in this series. But let's take a diversion and briefly review this again. The digital signal is actually a series of very low voltage pulses, each of extremely short duration, perhaps microseconds. For example, with this signal, the positive pulse represents the digit 1, while the negative pulse represents 0. This signal would represent the binary number 1001. Note that in this arrangement there is a rest period between each pulse. Another system relies upon the duration of the signal irrespective of the polarity. This particular message also represents the binary number 1001. The numbers 1 or 0 are convenient to use in a computer because they represent the on or off condition of a circuit. By closing or opening the switches in a group of circuits, we can easily represent a binary number, which is composed of ones and zeros. But how does this compare with our normal decimal system? Well, of course, the reason we use decimal is that we were born with 10 fingers, and we become accustomed to using the 10 digits in a numbering system to make up a message. In the binary system, it is the combination or sequence of ones and zeros which make up the message. Each of these ones and zeros is known as a binary digit. That is, a bit. In an 8-bit computer, the binary number would look like this. It is readily apparent that we can create a very large number of combinations of ones and zeros to produce different messages or characters or numbers depending upon the programmer's code. For example, this binary number, 1101111, is actually equal to the decimal number 219. Using standard conventions, negative numbers can also be handled. Of course, many of today's computers work with 16 or even 32-bit processors, with the consequent ability to use much larger numbers and provide more accuracy. In fact, a 32-bit binary number can represent a decimal number as large as, wait for it, 4,294,967,296. Wow. So it is a digital representation of the measured analog value, which is inputted to the respective circuit board in the microprocessor. Okay, now let's look at other inputs to the RTU. These are status indicating points. These signals are already digital in nature, that is, on or off, but an interface is still required in order to condition the signal. Surge suppression is required in order to prevent any voltage spikes or other interference getting into the main processor and causing damage. As before, these digital signals are fed into the corresponding printed circuit board to continuously update the RTU memory. Another input signal is in the form of pulse accumulation, which represents megawatt hours and megavar hour measurements. This information is then processed at regular time intervals, say 15 minutes or 1 hour, to produce data on energy transfer to interconnected utilities or large customers. There is yet a further interface, and this is for outgoing control signals. When commanded by the RTU, this circuit board will send out the required signal to open or close interposing relays, which in turn activate circuit breakers and other devices. In a similar fashion, output control signals may be sent out to raise or lower tap changers or generator load set points. This type of control signal is usually in the form of pulses. Another method uses the timed closure of specific control relays. These circuit boards, that is, analog input, status input, pulse accumulation, and control outputs, are all connected to the RTU microprocessor, which in turn controls the operation through software. This is mainly concerned with transmitting information from the RTU memory to the master computer when requested, determining which particular values are to be reported as exceptions, defining the sequence of reporting, that is, alarms and change of status first, detecting alarm conditions by comparison with set points, acknowledging control commands from the master computer, executing control commands from the master computer, in some installations exercising control action, such as load shedding, directly as a result of measured conditions referenced to internal programming. In some installations, printing out a sequence of events report. The RTU microprocessor output is in the form of digital signals. However, the very low voltage DC pulses cannot generally be transmitted over long distance. An exception to this is in communication via fiber optic channels. However, most current installations use leased telephone lines. Therefore, the digital signal must be modulated to an AC signal, usually between 500 and 3500 hertz for transmission, and then demodulated at the other end. This is achieved by installing a modem, that is, modulator-demodulator at each end. The most common type employs FSK, that is, frequency shift keying. The high frequency for a very short period represents the digit 1, and the lower frequency represents 0. Recall, FSK was discussed in PSP Tape 10 on pilot protection and PSP Tape 13 on power line carrier. Another method uses AM, amplitude modulation. In this case, the AC signal for a few cycles represents the digit 1, while no signal represents the digit 0. In yet another arrangement known as PSK, phase shift keying, the phase angle of the signal is shifted to indicate a specific arrangement of digits. In fact, this system can be configured to transmit 2 bits at a time. For example, when the phase angle is 0, this is taken to represent the digits 0, 0. At 90 degrees, it represents 0, 1. 180 degrees represents 1, 0. And 270 degrees represents the digits 1, 1. Because each transition represents 2 bits, this method will transmit information twice as fast as simple FSK or AM. The bit rate is a critical factor in Scada performance. More bits per second means that a greater amount of information can be transmitted within a given time period. The rate of data transmission is indicated by the term baud. A specific communication channel and its modems have a maximum practical speed of data transmission, say 1200 baud. This speed is determined by channel bandwidth and signal-to-noise ratio. However, be aware that the type of communication equipment can significantly change the effective rate of communication over a given channel. Nowadays, various schemes are used to increase the effective rate of transmission to 9,600 baud and even higher. Even so, it will still take several milliseconds to transmit an RTU message across this communication link. Compare this with the rate of digital transmission within the computer hardware, which is less than a microsecond. An improvement in the rate of information transfer can be obtained by time multiplexing, which effectively allows many RTUs to transmit over the same channel in the same time period. Further improvement can be effected by increasing the number of communication channels. Now, let's have a look at the format of the message being transmitted across this communication link. The typical binary message will consist of 3 parts. The first few bits alert the receiver that information transfer is about to begin. The center portion carries the coded information, and the last few bits terminate the message and perform security checks. Here is an example of a 32-bit message. The first 2 bits allow for synchronization of the receiver and transmitter, and the next 4 bits contain the specific RTU address. All of the RTUs on the same communication channel will read this signal, but only the addressed RTU will decode the message and respond. The following 20 bits contain the message. If this is the second message in a sequence, then it is not necessary to repeat the RTU address. So 24 bits of data can be sequentially transmitted until the message is completed. The coded message contains instructions for the RTU. For example, request complete scan of data points. Request report by exception. Control command, including the address of the specific device. Request maximum demand information for a specific interconnector. Once the transfer of information is completed, the message will be terminated by applying a security code followed by a sign-off signal. There are several different types of security code applied, all with the objective of detecting any errors which may have occurred in transmitting and receiving the information. If the message transfer is incorrect, the operator will be alerted and a further attempt made at transmission. Now remember, the transmission of data takes place in both directions. A modem is, of course, required at each end, the RTU and the master station. In addition to processing the communication signal, the modem installation should serve to isolate the computer systems and protect them from lightning surges which could occur in the communication link. The most common form of communication channel is the voice-type leased service. This may be connected in a party line arrangement where one channel is used to communicate in turn with several RTUs located in one substation. A more reliable configuration uses a separate communication channel and modem for each RTU. This also permits faster transfer of information. Now remember, we've been looking at typical RTU facilities and arrangements. Make sure that you become familiar with your own installations. At this point, it's time for a well-earned break, and then we'll come back and take a look at the master station. For now, please switch off the tape and thoroughly review this material in your workbook. From all we've said up to this point, it is clear that the master station has many functions to perform. It may consist of one large central processing unit, CPU, which performs all computing functions. This is connected to peripheral devices such as printers, CRTs, modems, etc. Alternatively, the installation may consist of a host computer, CPU, interconnected with other computers which perform specific functions. Many different configurations exist. As we go through the following description, please try to keep the various functions in mind rather than the specific device or physical location. Let's look at a generic system in block diagram form. The heart of this master station is the CPU, which in different installations may be called the master computer or the host computer or some other designation. This unit carries the operating instructions for processing and communication between other peripheral computers. It receives information, processes it, and issues operating commands to connected devices. One of these devices is the memory, typically a 200 megabyte hard disk drive. Along with this, there is often a small, say 40 megabyte cartridge disk drive. In this case, the cartridges can be removed for storage. Another important device is the clock. This is important as many of the operating functions are related to time. This master timepiece is usually synchronized to the neighboring power systems, which in turn are probably all synchronized to the national time standard. One main function of the master is to transmit and receive messages, and this is achieved through the communications interface. At this interface, one or more communications controllers are connected to the RTUs in the remote locations. This front-end controller is typically a microcomputer such as the one you see here. Generally, the communications controller performs the following tasks: modulates or demodulates the communications signal, In some installations, this function may be performed by a separate modem. Scans the RTUs and temporarily stores the data. Converts the incoming signals to computer language. Checks the values against established limits to trigger an alarm for abnormal conditions. When the scan is complete, say every few seconds, transfer data to update the CPU memory. This will normally take a few microseconds. Transmit operator control commands to the RTUs, including the SBO control check sequence. In order to achieve the rapid updating, several communications controllers are required so that communications channels can work in parallel. Another vital function of the master station is the operator interface. This is often effected through another computer called perhaps the display computer, or display generator, or man-machine interface. This in turn feeds several display stations, each with their own serving computer. We'll be looking more closely at the operator interface in the next segment. We've already mentioned that the stored data can be manipulated and used to provide valuable engineering reports. This is usually performed on a dedicated computer with associated printers. Again, this will have direct access to the memory bank. Yet a further workstation may be provided to carry out maintenance checks on the operation of the system. The CPU and peripheral computers are interconnected and communicate with each other through a network such as Ethernet or DataNet or some other supplier system. In essence, this controls the intercommunication protocol by instructing specific computers when to listen or talk. On most major control systems, it is usual to duplicate all of this equipment by providing a hot standby, that is, a redundant master station. This unit is up and running and ready to take over immediately if any failure is detected in the online computer system or peripheral equipment. Here we see a typical arrangement. Note that the standby system completely parallels the online system. For example, the communication circuits feed into both systems, and the display consoles are connected to both units. The operating system is monitored continuously, and at the first sign of component failure, switch over to the standby unit is automatic. This is often referred to as the failover system. Quite often, the standby computer is used for other tasks while it's offline. For example, training of operators, general purpose software development, inputting or modifying information stored in the computer, that is, the database. Of course, this work will be immediately interrupted when failover takes place. All of the computer operations and functions are performed by the application's software. A typical list of Scada software programs is included in your workbook. These packages are designed into the computers by the equipment supplier according to the specific requirements of the power system. However, facilities are provided to allow modification or addition of programming, logged reports, set points, and so on. One example would be the database which resides in the memory. This must be updated as new equipment is installed or ratings are changed on existing equipment. Another case would be modification of alarm set points or the deadband for exception reporting. We know that the computer has a very large number of tasks to perform, and consequently, the different software packages are competing for computer processing time. The computer works very, very fast, say in the order of 20 million instructions per second. Now that's less than a microsecond per instruction. Compare that with the rate of signal communication, which is close to 1 millisecond per bit, perhaps 20 milliseconds for each message. Because of this very high rate of performance, the computer can process several activities at the same time, or rather it appears to do that. In fact, it performs a small part of one task, then a few microseconds later a small part of another task, and so on, before returning to continue the first task. The various tasks are given priority levels. This means that if a critical message comes into the computer, say an alarm or breaker trip, then this is allowed to interrupt the processing of a lower priority task. When the priority function has been handled, the computer will continue to process the original lower priority activity. Actually, the allocation of computer time and resources is controlled by the computer's operating system, often called the executive program. This program ensures that all demands for service and the corresponding software operation all run in an orderly manner and in the correct priority. It also controls transfer of information in and out of the memory. It also takes care of all of the functions which require timing. For example, regularly scheduled tasks such as a 2-second scan or a weekly report. This executive software program also provides diagnostic information in the case of a failure in the system, and as part of this function, it executes failover to the standby computer. Now, in this segment, we have taken a general look at the main station tasks and the general arrangement of components and interfaces. As we said at the beginning of this segment, there are many different master station arrangements, but most have similar functions and objectives. For example, you may find in some systems that certain peripheral activities are performed in the CPU itself instead of using external subcomputers. You must make sure to study and thoroughly learn your own system. Now, we have quite a lot to say about the operator interface, so we'll first take a break. Please, switch off the tape and review this material in your workbook. The most impressive feature of the operator interface is the workstation with its display CRTs. Usually there are several display stations, each devoted to a different aspect of the operation, such as generation, interchange, system configuration, load transfer, etc. From here, the operator can issue instructions to the system through the keyboard. For example, he may instruct the system to display values for any metering point on the power system, display the status of equipment, such as circuit breakers, display in graphical form the power system and components of the power system down to substation level, receive and acknowledge alarm signals, display a list of outstanding alarms, instruct an RTU to carry out a control operation, for example, to open or close a circuit breaker, raise or lower transformer taps, raise or lower generator set points. Instruct the printer to log and print out specific information. The display will also respond to instructions issued by the computer when it's necessary to draw the attention of the operator. For example, an authorized or automatic change of status of any device, for example, the tripping open of a circuit breaker. An alarm condition when a metering point moves outside its preset limits. An error message indicating a fault inside the Scada system itself. This may be software or hardware. All of the above signals produce a flashing image on the CRT screen and also sound an audible alarm to attract the attention of the operator, who will need to take some remedial action. The heart of the operator interface is the display computer or display executive, which controls the operation of all of these programs. Let's look at this in block diagram form. The display computer is connected to the host computer or CPU, and from here it receives information which is then made available for display on the CRT. As we already mentioned, the particular display required is requested by the operator at his workstation keyboard. Remember that the host computer memory is being continuously updated every few seconds from the RTUs. And it's this continuous update that appears on the display screen. Control commands will be inputted at the workstation by the operator. In issuing a command, two actions are usually required from the operator. The first consists of identifying on the screen the specific area or device to be controlled. This may be done by using a light pen or by moving a cursor on the screen via a mouse. In either case, the coordinates of the point are located and the device identified. The second action is to press the specific button on the keyboard in order to command the required operation. This signal will travel through the display computer, through the CPU, through the communication controller, and out to the RTU. The control check signal will return over the same route to be displayed up on the CRT screen. One or more printers are usually connected to the display computer in order to carry out logging functions on pre-scheduled programs or as requested by the operator. In many control rooms, a large map board is installed indicating the major transmission lines, generating stations, and substations throughout the power system. This map board is usually equipped with indicating lights showing equipment status and perhaps some indications of power flows and voltages. All of this information is provided through the display computer. Nowadays, with modern technology, a multitude of displays are possible, so allowing us to view various areas of the system in close-up. For example, the operator may initially look at the overall power system, which would show the main transmission lines, generating stations, and substations. He can then call up a smaller area of the system to gain more information on that area. Depending on system size and complexity, and the information stored in memory, he may be able to call up data on a single substation or piece of equipment. When the operator wants to know the hot or cold status of a transmission line or transformer or other piece of equipment, he can request a list of data attributes for that specific item. Other status lists are available. For example, here we see the status of the various generation devices on this system. The generators are color-coded to indicate their current status. In this company's color scheme, green indicates units that are presently online. Red indicates units that are shut down but very quickly available, say in 15 minutes. White shows units that are shut down and not currently available, probably due to maintenance. Yellow indicates hydro units that have no water going through their turbines but are spinning from the system and are used as synchronous condensers. They are considered part of the readily available system capacity. The most interesting point here is the T. When this is highlighted, it means that the equipment is tagged. The operator can then refer to the CRT display in order to check which specific tags have been placed on this equipment. For example, a clearance tag to allow maintenance work to be performed on the equipment. In this state, all supervisory control will be prohibited from operating the switching devices. A local control tag. This indicates that the supervisory control has been lost and the equipment must be controlled locally. A warning tag. This draws attention to any special operating requirements that must be observed prior to operation. Most of the activities that we have looked at so far must be initiated by operator input. However, in the case of alarms, the action will be triggered automatically so as to draw the operator's attention to a changing or perhaps abnormal situation. An audible alarm will sound, and the specific alarm condition and location will be indicated on the CRT screen. This alarm indication may take various forms. For example, the station name will flash on the CRT control station diagram. The station name will also flash on the CRT alarm menu. The specific device on the CRT diagram will flash either red or green for a circuit breaker and perhaps yellow for a telemetering point. The alarm message is added to the current list of alarms. As with all alarm systems, the flashing lights and audible signal will be canceled when the operator acknowledges the alarm. However, the alarm indication will remain until the specific condition has been corrected. The alarm will be triggered by one of the following conditions: change in status, for example, an unauthorized breaker trip or reclosure; a telemetered value moving beyond the set point of its normal operating range; a calculated value moving outside of its set point limits. The alarm signals are all derived from the RTU measurements, which are scanned and transmitted to the master station every 2 seconds. Recognition of the alarm condition may take place in the RTU, or the communication controller, or the CPU, depending upon the specific equipment design and the particular measuring point. Calculated values are also obtained from measured quantities to provide or infer additional information. Operation of the Scada system itself is continuously monitored and alarmed in case of any failure in the RTUs, the communication links, or any other components of the system. Transmission of an incorrect message will also be alarmed. The operator has the facility to disable alarms from any specific piece of equipment. For example, perhaps the equipment is undergoing test, with the result that many nuisance alarms may be activated. Of course, here we've been looking only at typical features of the alarm system. Your particular installation may have many more features and types of alarm. Make sure that you become familiar with your own system. All alarm conditions are automatically printed on hard copy by the logging system. This system provides a printed record including the time reference of all operating events which occur in the power system, such as all status changes, authorized and unauthorized, alarm conditions and return to normal conditions, control commands and consequent action, any change of telemetering limits by the dispatcher, any changes in the status of generating units, details of load shedding activity, the placement or removal of tags from equipment, failure of any master station hardware, failure of any RTU or communications circuit. All of these messages are recorded on disk before printing so that information cannot be lost while queuing for printer availability. Most logging systems have several printers. In addition to logging events, other printers may record hourly and daily logs or any other log as requested by the dispatcher. For example, the trending of a set of analog readings for a specific piece of equipment. Clearly, the Scada system can do a tremendous amount of work to help the system operator perform his job well. By the same token, in order to take full advantage of the system, it is necessary to spend time in learning all of the details and features of your own particular system. Also, it's important to keep the Scada system operating correctly through a system of regular maintenance and inspection. And we'll be looking at this subject in the next segment. For now, please switch off the tape and review this material in your workbook. Now, in this segment, we're going to look at typical installation arrangements and maintenance requirements. Let's start first with the RTU. The fact that RTUs are located in remote stations already suggests a problem when it comes to housing the equipment. Many control house structures are not particularly substantial or even completely weatherproof. This means that the panels and cabinets containing the Scada equipment and terminal interfaces should be made as weatherproof as possible, complete with heating strips. Also, most of the components should be hermetically sealed to keep out moisture. In a typical RTU installation, you may find 3 or 4 different panels, one for the transducers, one for the Scada equipment itself, another for communication equipment, and the 4th for outgoing control relays for switching circuits. In some installations, the transducers are independently mounted adjacent to their associated measuring devices. but it is more common to mount all or most of the transducers in one panel and hardwire these to their respective terminals at the Scada panel. These signals may be subject to serious interference from electrostatic or electromagnetic surges from the power equipment. So special arrangements are usually employed for shielding and grounding. Make sure that your specific installation complies with its particular design requirements. Generally, the transducer cabinet requires a source of power for operation of the transducers. This supply should, of course, be a non-interruptible power source, similar to that for the RTU. The RTU itself is usually powered from the substation battery, which is normally 48-volt or perhaps 125-volt DC, floating on a continuous charger. A DC to DC converter is used to provide the specific voltage required for different RTU components. This also provides isolation from any spikes that may appear on the battery voltage from the charger. Where RTUs are some distance from the substation battery, 120 or 240 volt AC power from the local distribution supply is supplied and rectified in the RTU. In this case, an internal backup battery is provided. The various RTU components, such as the logic chassis, the printed circuit boards, the input and output terminal strips, and other peripheral equipment are often mounted in the same cabinet with convenient access for test and inspection. Located nearby will be the communications cabinets, which include such items of equipment as modems, surge arresters, transmitters, receivers, and multiplexing equipment when this is used. A well-designed RTU should be provided with an interface to assist maintenance personnel in troubleshooting. This is often called a man-machine interface, or MMI. It should be equipped with indicating lights or other indications so as to help identify which components of the RTU are not functioning correctly. It should also allow for isolation of specific control outputs by a local remote switch or control disable switch. This will enable us to test sections of the RTU without tripping circuit breakers or other control functions. Troubleshooting should be possible without disassembling the RTU. To achieve this requirement, certain test points and adjustments are made easily accessible and clearly marked. All of the printed circuit boards, the board slots, and other modules should be labeled for identification, as this will assist in substituting faulty components. Most RTU equipment suppliers provide portable test sets. These can be plugged into the RTU to function as a substitute master station in transmitting or receiving messages. Most of the tests are in the form of functional tests. A test signal is injected into different sections of the RTU, and the response is measured. For example, to check for correct operation of the encoder and decoder unit. To check the RTU's response to its address code. For adjustment, this code is normally set by dip switches on the appropriate printed circuit board. Check the response to control commands injected by the test set. Check that the address code for each equipment point is correct. That is, that output control commands operate the targeted equipment relay. Check the automatic acknowledge code. Check the status input from breaker alarms and other devices. This is done by simulating changes in status. Check the RTU response to a simulated request from the master station for full scan or partial scan. Most of the maintenance activities are involved with tracking down faulty logic cards and replacing these with spares. The faulty cards can then be returned to the equipment supplier or perhaps to the company's own central workshop for repair and adjustment. Preventive maintenance generally consists of regular inspection for cleanliness, terminal board connections, and climate control. The power supply should also be checked to ensure that it really is uninterruptible. Also, at regular intervals, the telemetering measuring points should be checked and the transducers calibrated as necessary. When doing this, don't forget to check CTs and VTs and refer to error characteristics. Right. Now, let's take a look at the master station. The computer equipment is usually installed in the system control center, often in a separate computer room. It is essential that the room be equipped with reliable air conditioning to maintain controlled climate conditions. Power supply to the computers is provided by a battery bank, which itself is part of an uninterruptible power supply system. A standby diesel generator is usually installed in case of an extended loss of AC. The Scada system is an absolutely vital function that cannot be allowed even a momentary interruption. We have already discussed this subject of uninterruptible power supplies in an earlier videotape in this series. To carry out functional tests, it is usual to apply diagnostic software specially designed to troubleshoot master station equipment. Regular preventive maintenance is also performed on items of equipment which are subject to wear and tear, such as printers, loggers, chart recorders, keyboards, CRTs, disk drives, and tape drives. Maintenance of the software programs involves debugging and revising the program or updating to meet changes in the power system. This work is normally carried out by the equipment supplier or perhaps a special department within the utility company itself. It is essential that good maintenance records are kept. All test results, calibrations, and preventive maintenance actions should be logged and filed for easy access. In addition to this, installation and commissioning test reports should also be available to the maintenance technicians. It is extremely important that complete maintenance instructions are available, including drawings, schematics, and step-by-step descriptions of tests and adjustments which are required. It would also be in order to point out that reliable communication channels are critical, and many hours can be spent troubleshooting problems associated with them. In this regard, the protection of communication circuits, the need for cooperation, and communication with the telephone company is discussed in the tapes on telecommunication protection. Now, in this segment, we've been able to give you only a broad, generic description of Scada maintenance requirements. In fact, this whole videotape is aimed at drawing your attention to areas where you will need to seek detailed information. Scada systems are becoming larger and more complex, covering a great area of the power system and fulfilling a large number of vital functions. To give you just an idea of the potential scope, we are including in your workbook a typical list of functional requirements that may be specified for a particular Scada installation. You'll need to spend considerable time in studying the fine details of your own particular installation. Please switch off the tape now and review this material in your workbook.